science on. You know, where do you go to find models, to find things that might represent the way the world works and so on? And sort of the traditional view has been you go to mathematics to do that. What I'm saying is that if you go to the sort of computational world of simple programs and so on, there's a much richer vein to look at.
Just to stop you only because I suspect I'm where the audience is. I want to understand, and it's important, and at the same time, I'd rather go slow rather than fast and suggest that I didn't understand or understood. You are saying that what you found is that if you wanted to explain the way the world works, what created order, what created other things, you needed to look at programs, like computer programs, to explain it.
Yeah, let me show you. I have an example. One of the big questions is sort of, if you have a very simple program, what might it do?
Right.
You might think if the program is really simple, it's always going to do something very simple. Here's an example of how this works. This is a program, it's called a cellular automaton.
Right.
And you have a line of cells that are either black or white.
Right.
And then in successive steps, it just evolves down the page.
Right.
There's a very simple rule here that says what color a particular cell should be based on the color of cells on the step before.
Right.
You start off with one black cell. In this case, you get just a very simple uniform black pattern. Okay, so it was a simple program. You started it from something simple. It made something simple.
Right.
This is kind of what we would intuitively expect. This is what I would have expected before I started doing the computer experiments I did.
Right.
So then the question is that always how it works, or can other things happen? So this is another example. Here's just another one of these programs. We started off from one black cell up here, and then we let it run for a while, and this is what we get. This is something much more complicated.
Yeah.
Still, you can see some regularity. This ends up being one of these so-called fractal or nested patterns in the end. But this is, again, something which where we can already see that even though the rule is very simple, the pattern we get is slightly more complicated.
Okay.
Okay. The thing that was really sort of the thing that really made me realize that there was something more going on that I didn't understand was something that I first saw in the middle of 1984. And it's this picture. This is a thing that in the scheme for specifying these programs is called Rule 30. And the way this works, this is the rule, this is the whole program up here.
Right.
You started off from one black square here,
Right.
and then this is what you get. And what's remarkable about this is, even though it looks like you sort of didn't put anything in, you just have a very simple program, you put in one black cell, you get out this complicated thing here.
Right.
And this is something, this sort of violates our normal intuition, because normally when we think about sort of building things in everyday life, in engineering and so on, if we want to make something complicated, we expect that we need to go to a lot of effort to make that complicated thing. But this is a case where that's not happening. We have a simple rule, we have a simple initial condition, and yet we get something complicated. And it seems sort of, it effortlessly produces something complicated. What's, I think, particularly interesting about this is when we look in nature, we also see lots of complicated stuff that's been made seemingly effortlessly by nature. And so the thing that kind of really got me excited about this was the idea that perhaps whatever is going on here is also the essence of what's going on in nature and the way that nature makes complicated stuff. And that sort of, it was this sort of discovery that really got me started in the direction that's eventually led to all the science that I've done.
And this is called cellular automata?
Yes, this is the Rule 30 cellular automaton.
Okay. Now, you later began to look at patterns in shells and explain to me the significance of that.
So one of the questions is, there's the issue of when we see complicated things in biology, or in nature in general, how is nature making that complicated stuff? Does it have very complicated rules that it's applying as we might expect if we were going to make a pattern as complicated as that by some engineering process? Or does it have some very simple rule that for some abstract reason inevitably makes something complicated? What you find, well, for example, here's an example of a shell.
Yeah. Oh, wow. Yeah.
Where you can see the pattern on it is quite strikingly similar to some of these kinds of patterns made from the computer. And one might have thought when one saw a complicated pattern like this that the shell must have had some very complicated way to make this. The mollusk must have had some very complicated way to make this. Or perhaps that some elaborate process of evolution had sort of carefully controlled it to make this kind of thing. But what the things that I found suggest is that, in fact, you can just have a very simple rule that might be sort of picked randomly in the space of possible genetic programs, and that sort of inevitably, even that simple rule can produce this complicated stuff.
What idea are you, I'm asking you to repeat yourself, are you getting from this?
Well, I think
First of all, other than simplicity.
Right. So one of the issues in biology, for example, is could there be a theory of biology?
Right.
Okay, from the sort of Darwinian tradition, one has the notion that what we see today is the result of a long series of historical accidents in evolution. The fact that it's this shell rather than some other shell was a consequence of some accident that happened to some mollusk in the Cretaceous period or some such other thing. Okay, and one sort of imagines that there can't be a theory in biology. But one of the things that's come out of what I've looked at is that, in fact, that might not be the case, that it might be true that sort of what's happening in biology is that biology is sampling a large collection of possible simple programs, and that it's sort of an inevitable consequence of it using simple programs that certain forms, behavior occur in biological systems. And so there's the potential from that of saying we can, to some extent, predict what we might see in biology, rather than just having to sort of wait and look at the historical and sort of imagine that it's something that's a consequence of historical accidents that we'll never be able to kind of address in a scientific way.
Today, after finishing this book, what's the biggest question for you?
Well, there are many sort of in many different directions. This book has opened things up. So, for example, in physics, one of the things that I've been interested for a long time in sort of fundamental physics and what kind of underlying theory there might be for the universe. One has imagined, by looking at sort of the history of progress in that question in physics, that if there is an underlying theory of the universe, it must be something very, very complicated. Because it seems like every time you kind of peel down to a smaller scale in physics, the equations get more complicated, everything gets more complicated. From the things I've seen, I kind of got the hope that perhaps it might not be that way, that instead there might be some very, very simple underlying rule that produces all the complexity and richness that we see in our universe. So one of the things that I tried to do in the book was to try and see what might that rule really be like. And one of the things one realizes
that explains the universe.
That explains the universe. So what I'm interested in there is, could there be some simple program, some simple set of rules that if you run it for long enough will reproduce in precise detail everything that we see in our universe. And if I hadn't observed the things that I observed from the computer experiments that I've done and things like that, I would never imagine that that could even conceivably be possible.
And now you believe. Go ahead.
I'm very convinced that not only is it possible, but that it's almost certainly true, and that one day, perhaps even soon, there'll be a time when we'll be able to say this simple set of rules, this is our universe. And there's a question of sort of what might those rules be like, and what kinds of things, how familiar or not might they seem. So even things like space and time, which seem to us now sort of intuitive concepts, you have to kind of break them down into something smaller if you're really going to pack our whole universe into a small rule.
Go ahead.
So for example, in the case of space, we sort of imagine space as being kind of this continuous thing where you can move through it continuously. In kind of the way that I imagine things might be, space is instead much more like at a very small scale, like a kind of network where you just have these points that are connected in a certain way, and kind of at the lowest level, there isn't anything that sort of looks like space as we know it. It's kind of like in water or something.
Yeah. No, go ahead. I'm sorry.
It seems like kind of a continuous fluid when you just look at water in a glass. But if you look at what's underneath, it's a bunch of discrete molecules bouncing around. And so similarly, I suspect that in the case of space, there's something a bit like that going on.
Let me try to make an analogy and tell me whether it means anything, even as a question and with respect. The people that map the human genome have said to me, and all of them that were involved in this, all of the leaders, have said to me, to a person, while genes are destiny, it only explains 50% of it. 50% of it is environmental. What's the equivalency of that idea in terms of what you are talking about, in terms of a certain set of rules? Is it chance? Is it accident? Is it something else?
Well, so one of the features of the kinds of rules I'm talking about is that once you've set up the rule, what will happen is always the same. There's no chance to kind of get sort of environmental effects coming in from the outside. But one of the things that's interesting is you might have thought once you know the rule, you know everything about what's going to happen. And but the sort of the big thing that comes out of what I found is that that's very, very far from being correct.
Now, why?
Well, okay, very good question. I spent a long time trying to figure that out, and I think I now know the answer.
All right.
So the issue, it's a little bit of a long story, but the question is, given the rule, you produce some behavior.
Right.
Now, there's an issue of kind of, can you foresee what that behavior will be from the rule itself? Now, if you could foresee it, what it means is that you, with your brain, with your mathematical computational methods or whatever, can in a sense shortcut what the system itself is going to do. So let's say the system itself is going to run for 1 million steps. If you could foresee what was going to happen in it, what that means is that you, with sort of less effort than those 1 million steps, could say, the system, it may take the system a lot of effort to find out what's going to happen, but I can know that after 1 million steps, the result is going to be this. And that's, in a sense, most of traditional exact science is based on the idea that one's able to do that. So, for example, a typical thing is when you look at, let's say, the idealized model of the Earth going around the sun. Right. You get some mathematical formula which says where the Earth is going to be at any time. And what you can then do is, if you want to know where's the Earth going to be 1 million years from now, you can just plug some numbers into that formula and immediately answer that question. You don't have to trace 1 million orbits of the Earth around the sun to find out what's going to happen. But in a sense, what that assumes implicitly is that you, as a predictor, as an observer, are somehow computationally more sophisticated than the system itself. While the system itself had to go through its 1 million steps or some such other thing, you, as a predictor of the system, were sort of able to be smarter than it and to figure out what it's going to do without going through all the effort that it had to go through. This is an idea that I call computational reducibility.
All right.
So now here comes the crucial point.
All right.
The issue is, how do we, our brains, our computers, things like that, how do they compare in their computational sophistication to these simple programs and things like that? And the crucial thing is this thing that I call the principle of computational equivalence, which is the idea that, in fact, these systems are equivalent in their computational sophistication to us as observers. So what that means is there's sort of a competition between the system itself doing its thing and us trying to predict what it's going to do. And we might have imagined that we were always sort of so computationally superior to these systems that we could work out what they were going to do much more easily than they do it themselves. But this principle of computational equivalence implies that that isn't the case, that instead that there's a computational irreducibility to the behavior that one sees, which means that if it takes, let's say, 1 million steps for the system to do such and such a thing, we're not going to be able to work out what it's going to do by any procedure that's much more efficient than essentially just running it for 1 million steps. So what does that mean in the case of something like biology?
Right.
What that kind of means is that if you have given the genetic program, you might say, okay, once we have the program, we've solved the problem. Because once we have the program, we know everything about what's going to happen, let's say. What this is saying is that even given the program, it can still be hard to tell what's going to happen. Even given the program, knowing whether this particular program is going to lead to an organism that only grows for a while and then stops, or to an organism which keeps on growing forever, or something like that. To answer questions like that may be sort of irreducibly difficult. And the only way to do it, in a sense, may be to just sort of run the program and see what happens.